one of our youngest faculty members, Dr. Sarah Lee. Sarah got her undergraduate degree from University of Science and Technology in China in 2003. And then she got her PhD from UC Riverside in 2010, followed by 2 years of postdoctoral training in Los Alamos. I have had the privilege of sharing a floor with Sarah in the faculty area for the past couple of years. And what really fascinates me about her work is her healthy obsession with noise. So I think that we share in common. And without further ado, I'll ask Sarah to take over. And thank you.
Thank you for the introduction. I've been here for 3 years. I think this is a good opportunity for me to give an update on the research we have been doing. Today I will talk about exciton spin dynamics in hybrid organic-inorganic perovskites. So the key words here are actually spin and perovskite. This is a curve that we typically get from the ultrafast optics measurement. You see the signal is really clean, almost no noise. So today okay, I will try to speak louder. The microphone is for a recording, not for...
Oh, it's for recording.
It's only for recording. I'll try to speak louder. And this oscillation typically means spin precession in magnetic field. And the main message here will be we demonstrate in this hybrid perovskite for the first time we can realize this type of oscillations in this material. But of course, I will spend the next hour to tell you the detailed story. This is an outline. First, I will give the introduction on hybrid perovskites and the spintronics. Then I will discuss the experimental techniques, then continue on to our results and the interpretation, and finally some future work. Okay, I believe that many of you already know this material because a lot of us in the department are working on the system. This material is a hot material in the field of organic photovoltaics because the solar cell efficiency now reached 22% by using the perovskite, specifically methylammonium lead iodide as an absorbing material. And this material has the structure of a perovskite like the calcium titanium oxide, but here this A stands for the methylammonium, the organic ion. And this is also the material that we're going to focus on today. So if we look at the photo conversion process in the solar cell, we know that a photon shines on the material and creates electron-hole pair. Electrons get collected by the cathode, and the holes are collected by the anode. That gives electricity. So in this process, we know that it's only possible because of the excellent optoelectronic property of the perovskite here. For example, it's an excellent light absorber. And the long carrier lifetime and the high carrier mobility facilitate electron-hole pair dissociation rather than recombination. And it's amazing that all these excellent properties are realized on materials that's processed with solution. That means you just mix solution and a spin coat, nothing high technology. You get these nice properties. Okay, it's also worth mentioning that it's a series of material. For example, by substitute the iodide with bromide, you can reach tunable property. Say the band gap increases from near infrared to the high end of the visible range. So that means we can reach tunable properties by chemical substitution. Okay, that's a brief introduction about the material. And we have the perspective from spintronics. And I would like to talk about spintronics for a little bit. Spintronics aims to use electron spin in addition to the charge for information storage and processing. The natural spin up and the spin down can represent the binary information of 0 and 1. And for that, you can have non-volatile and high-density memory devices. And that's the theme of metal spintronics. And also, you can do logic operations based on spin. Switching spin direction is faster than moving charges and also costs less energy. And that's the main goal of the semiconductor spintronics research. And I would like to talk a little bit more about the device application here. For example, the spin transistor. Generally, a semiconductor spintronic device are composed of the input and output electrodes and the medium that's connecting those two electrodes. And the medium is usually semiconductor. And ideally, we would like to manipulate the spin or rotation through external gate. And we can see that the requirements for the semiconductor here are the following. We need to have long spin lifetimes so that the spin information is conserved by the time the carrier transport to the drain electrode. And also, we would like some effective ways to manipulate the spin. Okay, but both these two goals are kind of competing because they both relate to spin-orbit coupling. Large spin-orbit coupling would help the spin manipulation, but it also relaxes spin. But is it possible to have both with a simple bulk material? Of course, people have been trying different schemes or clever device designs to overcome those limits. But is it possible to have both property in one simple bulk semiconductor? And I hope you get some idea by the end of my talk. Okay, now let's examine the hybrid perovskite for spintronics application. The materials are predicted to have large Rashba spin coupling for spin manipulation. What this means is the following. So the electrons feel some effective magnetic field as a transport. And that effective magnetic field is perpendicular to the electric field direction and its momentum direction. So imagine that you have a spin polarized electron. As it moves towards the right, it precesses about that effective field. In that way, you reach spin manipulation. Okay. In terms of the band structure, spin up and the spin down electrons in the y direction, they have different energy because of that effective field. And you reach Rashba band splitting like that. This is possible. It's large in this perovskite because there are lead and iodide, which are heavy atoms that have a large spin-orbit coupling, and also in the material because the ordering of the organic ions, there is a inversion symmetry breaking. Okay, that's theoretical prediction, and recently, very recently, it has been demonstrated by RPS measurement, the angle-resolved photoemission measurement in one of the perovskite materials. And like I mentioned before, the properties of perovskites are tunable by chemical substitution. For example, again, the same series of material, by substituting iodide with a lighter atom of bromide, we expect lower spin-orbit coupling, which is a key parameter for all the spin-dependent processes. Okay. So to really talk about the experiment, how the technique works, we also need to look at the band structure. This shows a band structure from first principle calculations. So the main features, I just mentioned 3 of them. First one, the band edge states are from the inorganic frame. For example, the conduction bands are p orbitals of lead, and the valence bands are 6s of lead and p orbital of iodide. It's their hybridization. There are very large spin-orbit coupling in the conduction bands. And because of the symmetry of the bands, we have spin-dependent optical transitions. Okay, to simplify that picture, we have S-like valence band and the P-like conduction bands. They split because of the spin-orbit coupling. Now we have J of 1/2 and J of 3/2. The band edge states are J of 1/2 conduction band and S 1/2 valence band. Because of that, now with circularly polarized light, we can choose to excite only specific transitions. With right circularly polarized light, we excite from the negative 1/2 to positive 1/2. With left right circularly polarized light, we excite from positive 1/2 to negative 1/2. And that change of angular momentum comes from the photon. That one change of 1 comes from the photon. And I would also like to mention that the material experiences phase transitions as temperature cools down. The symmetry gets lower from cubic to tetragonal than to orthorhombic phase, and we work with this low temperature phase. And the symmetry of the bands are still approximately like that, slight changes. Okay. So now I will talk in more detail about the optical transitions. So these are the bands. With right circularly polarized light excitation, we excite those populations. We have spin polarization in the conduction band and valence band. Similarly, with left circularly polarized light, we excite the other pair of states. So, but the measurement also works based on the same rules. Imagine that we already have some spin population in the valence band and some spin population in the conduction band. We can measure that with a linearly polarized light, which can be thought as equal combination of right and left circularly polarized components. Because of that population difference in conduction and valence band, then the absorption edge for the right and the left circularly polarized light are a little bit different. There's a little bit difference here because this corresponds to that energy here. And this is a lower energy for the left circularly polarized light. And accordingly, you also have a difference in the indices of refraction for those two. And Faraday rotation measures exactly that difference in the indices of refraction. So the phenomena is that with a linearly polarized light, you can have a rotation of the polarization plane by a small angle, and that small angle is proportional to that difference here, and also proportional to the spin polarization in the conduction and the valence band. Okay. So we do this measurement by excitation and probe in an ultra-fast optics measurement. Okay, here's how it works. With a right circularly polarized pulse, we create spin polarized electrons and holes. If we simply only look at one spin species, say spin half carriers, then it's a superposition of spin up and the spin down along the magnetic field direction. And that creates beating between those two states. In a classical picture, it is simply spin precession about the magnetic field. by a linearly polarized pulse, we can measure that precession as a function of time, and we get oscillatory signal. And from that curve, we can get the precession frequency, and also from the decay envelope, we get the spin lifetimes. That's the main technique. Okay. So now let's look at our measurement on the hybrid perovskite. Here, this is how the sample look like. They look like black because it absorbs the whole visible range. And that's a SEM image. Doesn't look very flat. And that's XRD. And this picture shows the absorption curve and the photoluminescence. And we can see exciton absorption peak very well. Okay, we believe that it's excitons because of also a recent experiment that determined the exciton binding energy to be 16 millielectron volt for the low temperature phase. Here's our result. This is the data at 0 magnetic field. Then we increase the magnetic field in transverse direction, and we start seeing oscillations. So notice that the field are thousands of Gauss. And we see oscillations. You probably noticed 2 frequencies already. And that 2 frequency can be seen very well in the Fourier transform. So it took hours of effort to really get that signal.
Signal from experiment?
From experiment. These are from experiment.
That's nice.
That's real data. It's not simulation. And I would like to say that the fitting of the curve lays exactly on top of the data. So I don't need to show this fitting. It's real data. It took many hours to get that to that stage. And of course, then the next challenge is to explain what's going on, what we have observed. So let's first look at the zero field data. And it shows by exponential decay, this shorter time scale is 150 picosecond, and the long one is 1170 picosecond. So what are they? So we also look at the transient absorption, which we don't really measure the polarization of the light, but we just measure light-induced absorption change in the material. And we also see 2 time scales. And this small component has a short lifetime, also 150 picosecond well. And this is a much longer time scale component. And we consider that to be the cross-gap recombination or the exciton recombination. And this lifetime is much longer than 2 nanosecond or 2,000 picosecond. So now let's come back to this one. So we think that this short time scale component, it has the same origin as the transient absorption, which are from trap states, because that components disappear in the transient absorption. It disappear at higher temperatures. Okay, and this the other component that has over 1 nanosecond time scale. Now we consider that to be the real spin dynamics. And in here, the recombination time is much longer than the spin relaxation time. So we are really measuring the exciton spin dynamics. Okay, so I would like to claim that this 1 nanosecond is anomalously long for this material, because we know that the bad edge states are from lead and iodide, and these are really heavy atoms, and spin orbit coupling scales with a Z to the power of 4. And the sample, we already seen the SEM image, and we know it's solution processed. It's polycrystal film. consider those facts, we think that this is really surprising. And you may also wonder if 1 nanosecond is long or not. The fact that we have seen many oscillations, that means in within that lifetime, we can do so many operations already. So it is long. Okay. Then the next thing, we need to figure out what are the two frequencies. So here I plot the two frequency versus magnetic field. We can see that they are roughly linearly proportional to the magnetic field and go through the oranging, but not quite. Say the lower frequency, it has a little bit negative offset here. Okay. So then we need to figure out what those two frequencies are. First, we would like to identify whether it's excitons or free charges. And like I just mentioned, we assume it's excitons, but it's not obvious at the beginning. Luckily that we have that experimental determination of the exciton binding energy, we can pretty much say that at low temperature, the photoexcited species are excitons, dominantly excitons at the low temperature region. Okay, so we assume, okay, that's the right picture. They are excitons. Electron and hole have some interaction, Coulomb interaction and the spin exchange interaction. Okay, then the two frequencies must be from quantum beating of the exciton states. And we should describe everything in terms of the exciton picture. And the problem now comes down to what are the exciton states? What are the eigenstates? Okay, so if we consider spin only, if you have one spin half electron and a spin half hole, then classically you have 4 combinations. You have those 4 states, right? Up, 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 down, down, up, and down, down. Right? And quantum mechanically, you also describe in terms of singlet and triplets. Optically, only singlets are bright states because the angular momentum is not directly exchanged between the photon and the electron spin. You need spin-orbit coupling. So of course, we consider spin-orbit coupling, and that's a big effect in this material. When we consider spin-orbit coupling, we have the electrons to be actually represented by GA states, not spin states anymore. GA now is a good quantum number. Hole still stays as S-like. And further, we consider the spin exchange coupling between the electrons and holes, between the electron and hole, and also the crystal structure symmetry. And we consider the tetragonal phase here. And it has a point group of C4V. Based on the symmetry of the conduction and the valence band, and also crystal symmetry, we can figure out that those 4 states are the eigenstates, where the Psi 1 is dark, not optically active. Psi 2 is active with a linearly light excitation along the C-axis of the crystal. And then Psi 5 plus minus are active with circularly polarized light excitation in the AB plane. So, but in magnetic fields, that's really what we need to figure out, what the eigenstates are. So in magnetic field, those 4 states, they mix and split. And the energy levels of those 4 states depends on the strength of the magnetic field. Those are the 4 states. Say, and with 4 states, and you choose one pair, you have 6 combinations of choosing 2 from 4 states. That means 6 possible energy differences here. But with our optics measurement, using the Faraday rotation, only 4 of those are optically active here. And in the case of a small spin exchange coupling, those 2 differences are very close to each other. And though that difference and that they are also very close, so the 4 frequency reduced down to 2. And we thought that's what's going on in our measurement. We have 2 frequencies there. And by collaboration with a theorist, we basically he calculated the G factors for electrons and holes. And based on his calculation, and we realized, OK, this number is very close to the calculation for electrons. And that number is close for the calculation for holes, and with a minus sign there. Our measurements do not really tell the sign of the G factor. But based on his calculation, this is likely to have a negative sign there. And that's for electrons, and this is for holes. So there's also a small exchange coupling. Say, this is not exactly linear, right? There's a small bending at low magnetic field, and that explains that a little bit negative offset here. So this is not some artifact. It's real because we've measured many samples. There are cases this negative offset is even more, like say goes about here. But still, the exchange coupling are on the order of microelectrovolt. OK. What this means here, even with this complex description of the exciton states, the 2 frequency now comes down to for independently electrons and holes. So approximately, the picture is you can think that electrons and holes, they precess independently in the exciton. We like that picture as experimentalists. Okay. And further, I would like to show you more the phenomena we observe in the polycrystalline samples. As we increase the magnetic field, you probably also notice that the lifetime gets shorter, right? So we plot the lifetime as a function of magnetic field. It decreases very fast. It decreases, we thought it's dominated by spin dephasing. So initially, we oriented those spins all in one direction. But as they precess at slightly different speed because of the G factor distribution. As they precess even more, the distribution gets larger and larger. Eventually, if it's more than 180 degrees, they cancel each other. So that's why you get a decrease of the signal. And OK, we can assume that this pure distribution from the G factor, and we can estimate the G factor distribution here for both components. And the G factor distribution, we thought it comes from the crystal anisotropy. So G factor along the C-axis is different from the A and B axis. And also,
Is this the T2 from magnetic resonance, the spin relaxation time, basically?
yes?
OK, so what is T0 then?
We kind of assume this is a true spin decoherence time.
This would be T2, because that's T2 star.
That's right. Sorry for that confusion of the notation. So that stands for B at 0 field, say.
Oh, in 0 field.
Yes. But we typically, I don't really use that as spin decoherence time because it's not a direct measurement. It's like a fitting from assuming the dephasing only comes from the G factor distribution, but it may not be true. But if we really like to infer a spin decoherence time, so say this curve extends to something over 1 nanosecond at 0 field. Okay, so
So what you measure is actually a coherent dephasing.
yes, it's dominated by the dephasing, spin dephasing. Not this is not the true spin decoherence time. So that's why we call that T2 star. It's an ensemble measurement.
But the delta G is really a measure of how much the NMR frequency changes from spin to spin.
Yes.
So normally we would think of that as being the T2, the intrinsic T2. So I'm a little confused as to the difference between that term and T0.
Here I would say that it's dominated by spin dephasing because of the G factor distribution. But the true spin decoherence time would be you have only one G factor. So you have only one spin, how fast it loses its phase. That would be the true spin decoherence time. But at least we can kind of infer that the spin decoherence time is also long, at least longer than this time. Okay. And what I just described as exciton states, we have really two pairs of very close frequencies. That very close to frequency, they can also result in spin dephasing, extra spin dephasing. Okay. So I would like to summarize the relevant dynamic processes in our ultrafast optics measurement before I have no time of coming back to this. So here, after we excite with a circularly polarized light, we basically create spin imbalance in both the conduction band and valence band. Then there are three relevant processes. Here, electron can flip their spin, or it's not really pure spin states, but the states relaxes, and whole spin can flip. And also there could be recombination. The recombination is also spin dependent. Like in our measurement, we have determined that the recombination time is very long. So what's relevant are only those two. Or to be precise, it's spin polarized exciton states relaxation. Okay. Here, what I mean by spin dependent recombination are the following. Say, electrons and holes, they have different G factors. They precess at different speed. After precession for some time, okay, spin exciton states with a total angular momentum of 1, recombination is allowed and give out a circularly polarized photon. But a total angular momentum of 0 is not allowed. That recombination is not allowed. In our measurements, we haven't really measured anything related to recombination because the recombination is much longer time. We are dominated by spin dynamics of the excitons. Okay. So, but I have been talking about this spin dynamics in terms of excitons, but experimentally, at the early stage, we did need experimental evidence that they are truly excitons. Okay, so we did the kind of same measurement, but in a steady state fashion. We use continuous wave lasers, not the pulse laser. So the pump laser, it's at higher energy, higher than the band gap energy, and it's circularly polarized light. And the probe light has a narrow wavelength, and it's tunable. So now the measurement, since it's steady state, it's a time integration of all the spin signal in the past time. And we know that the time resolved data shows this is how it looks like in zero field, and that's how it looks in some external magnetic field. So as we do the integration, we get some positive signal. But for oscillations, they're going to cancel out. We get really decreased signal in magnetic field. As a result, we get signal, say, it decreases with magnetic field. And how fast it decreases from the width of this curve, from the width of the magnetic field response, we can also infer the spin lifetimes here. And that's typically a Hanle effect curve that we measured. So this effect, the spin cancels out in a steady state measurement, is called the Hanle effect. And this curve can be decomposed very well to 2 Lorentzian peak. And that we can, again, find out the lifetime. Say we assign this narrow peak to the component with the larger G factor, 2.6, and the wider component to the smaller G factor component. And we get lifetimes of hundreds of picoseconds. That's consistent with our ultrafast measurement. So it's all consistent. But what matters here is this energy dependence. So basically, we can get the amplitude of those 2 components measured as a function of energy. So those points are the experimental data. Basically, we change the wavelengths, we measure the curve. We change the wavelengths by small steps, we got those points. And this curve shows the absorption. And we can see that the signal tracks the absorption peak very well. That kind of confirms that we have the spin signal that originated from the excitons. Okay. That's an important piece of information. We experimentally really verify in our sample it has the excitonic origin. Okay. And by looking at the shape of this curve, I would like to remind you what we discussed as the energy dependence of the indices of refraction. We kind of have exactly this shape. So everything what we have measured so far just demonstrate what you expect theoretically very well. It's like the best signal that you can get from simulation. Okay. Further, I would like to discuss the spin relaxation mechanisms so that we do the temperature dependence of the measurement, the spin dynamics measurement. This is a spin lifetime as a function of temperature in a log-log plot. And we can see that it shows 2 regimes. For the high temperature above 15 Kelvin, up to 150 Kelvin, we see a power law dependence of T to the minus 1.5, roughly. And in principle, the temperature dependence tells us the scaling of spin relaxation with a momentum scattering. And that should give us some clue on the spin relaxation mechanisms. So here, let me discuss a little bit about the spin relaxation mechanism here. Because of the lack of inversion symmetry, it's possible to have both the Dirac-Perot and the Elliott-Yaffe mechanism. So the way that the Dirac-Perot works is a spin basically precesses about an effective magnetic field resulted from spin-orbit coupling between each collision. And that effective field kind of changes between collisions. And you have this motion narrowing. So that spin lifetime is actually proportional to momentum scattering rate. But in the Elliott-Yaffe mechanism, the spin relaxation is inversely proportional to the momentum scattering. But unfortunately, it's very challenging to measure the mobility of the material. Not only to us, but it's a challenging to the whole community, because the films, polycrystal films, have really large resistivity. We can not just fabricate a Hall bar and get the mobility. Okay. In general, for the films, it's very resistive. You put the voltmeter on, and it just says open. or we already tried to fabricate small devices by making Hall bars down to tens of micrometer, but still it's very resistive. Okay. So of course now we say that to figure out the spin relaxation mechanism, we need more theoretical work and also experimental work in the future. And in this material, it's also spin relaxation can also result from electron-hole exchange interaction. Although in our measurement, we kind of observe that electron and hole, they have a comparable spin lifetime, so that we can see the beating of the two frequencies, which are not commonly seen in bulk semiconductors. And of course, electron carrier-carrier scattering also results in spin relaxation. And we have observed that if you increase the excitation power, you get more relaxation. Further, we also have the temperature dependence of the spin dynamics in transverse magnetic field. That spin dephasing time also decreases with temperature. And also G factors, we see there's a pretty big change by increasing the temperature from 4 Kelvin to up to 60 Kelvin. For example, the electron G factor decreased by 0.2. And also the whole G factor, it changes from 0.3 to really small. Cannot be identified above 40 Kelvin. And this G factor change with temperature are not too surprising. If you consider, okay, band structure also changes with temperature. Band shifts, and the parameters of the band structure also changes, because the lattice parameter of the material also changes with temperature. As you increase the temperature, of course, the structure gets more symmetric. Okay, here's my conclusion about this part. We demonstrate optical orientation and the quantum beating of the exciton states in this hybrid perovskite for the first time. And we measure very long spin lifetimes, more than 1 nanosecond. That indicates that we have coexistence of a long spin lifetime and a large Rashba effect for spin manipulation. And hopefully you still remember the question I brought up at the beginning of the presentation. So this material, probably because of the intrinsic band structure, we kind of get over that limitation of both spin lifetime and Rashba effect depends on the strength of a spin-orbit coupling. Here we have both. The G factor of electrons and holes are first time determined explicitly to be 2.6 and negative 0.3. And the open questions are the spin relaxation mechanism. What are they? So why we get very long spin lifetime even in the presence of large spin-orbit coupling? What are the roles of the organic cations? So our work was submitted recently. For the future work, we would like to get the full picture of the exciton states that includes the exchange coupling and the anisotropy of the excitons. We would also like to study in more detail about the spin relaxation mechanisms by doing doping the material, by doing power dependence and changing all possible other parameters. And we would also like to characterize the Rashba spin-orbit coupling in this material by our optics techniques. And we could also tune the spin-orbit coupling by exploring materials with different chemical composition. And toward the device application, we would like to study spin generation in ferromagnet perovskite heterostructures. So I would also like to mention another direction of research in our group. I have only briefly one slide. We were interested in looking at the magnetism in two-dimensional materials with magneto-optics techniques. Because of the intrinsically predicted, the predicted intrinsic ferromagnetism in 2D material. And those materials are attractive for low-dimensional spintronics devices. Our optics techniques are especially suitable for these studies on, say, small flakes of material that's exfoliated by the Scotch tape method. And we have been able to measure the magnetic hysteresis on those thin flakes of chromium germanium telluride material. And that work was already under review with collaboration with our collaboration with a group in Peking University. Okay, I would like to acknowledge my group members and also my collaborators. The theoretical work was done. Insight was brought up by Zhi Gang from Washington State University. Samples are provided by Vali's group, and we also got the 2D material from a group in Peking University. And I like to thank the support from University of Utah and MERSEC. Thank you. Questions?
So in the story that you told, the Rashba in orbit did not play any role, really, right?
I believe it does play a role in the spin relaxation.
Apart from being a vest that causes spin relaxation.
Apart from that, it does not. I don't think it affects our. It creates any effect in our observed dynamics.
Presumably, that actually comes from the existence of this organic molecule, right? That's
Yes.
what causes that.
Yes.
So, is there any other effect of the organic molecule? Or in other words, maybe is it known why these guys are so good for solar cells? Or
Well, you see, because of the, I believe the spin dynamics also affect carrier dynamics or affects the recombination, right? That is relevant to the photovoltaic application. How the
what's so special about spin dynamics here that it's so great for solar cells?
It's not clear. So I just say that it might be relevant for the solar cell application because of the role of the organic ions. I mean, there are theoretical speculation that because of the organic ions, the band structure changes constantly from direct to indirect. And that's why the recombination time is very long.
But that
because of the
happens at lower temperatures only, right? So
that
those things to be ordered to have growth in inversion.
right, but the solar cell works at room temperature. The organic ions are rotating constantly at room temperature. That rotation gives a constant changing of the band structure, say from kind of direct to indirect, direct to indirect all the time. That may give long recombination time. That's one theoretical speculation. It's not really verified experimentally or something. Right.
Changing randomly usually is better.
So the role of organic ions, I think it's not clear by now what's how it's related to the special property of the hybrid perovskite. It's not really clear.
Why is exchange in these excitons so weak somewhere in the microelectron volt range? Does this have something, I mean, naively I would think with the, I mean, well, obviously there's not much.
Well, that I don't know, but say the exciton binding energy is not very big either. It's a bulk material. It's like 16 millielectronvolt. But the fact that, well, we measured as those offset of the precession frequency versus magnetic field, it's also very small on the order of micro EV. We have more measurements that shows larger offsets, but still it's in that order. We don't know the reason, say, why the, well, in terms of the size, okay, the exciton, electron and hole wave fraction probably have very little overlap. And approximately, you can even think as electrons and holes precess independently.
So my question, maybe to rephrase it, so
Why?
it's clear from your data that there's this offset, and you can explain it with some sort of spin interaction between your electrons and your holes. Does this have to be exchanged, or can it be something else?
I thought it's pretty standard that
I mean, it's something like a zero field splitting, essentially.
sure, the zero that is zero field splitting.
It is a zero field splitting.
Yes.
But what's the nature of it? Could it be dipolar coupling?
Yes, between electron and the hole. I mean, if they are spatially apart, yeah, it's dipole-dipole interaction. But yes, what we measure, say, what I said as micro EV range, that is the zero field splitting.
Okay.
Basically, the zero field splitting depends on the exchange coupling. It's some linear combination of spin exchange coupling in different directions. Please.
As far as the, you showed some data earlier in the talk where you had T2 decreasing as you increase temperature, which is exactly the opposite of what you would expect if you had motional narrowing, say, of the dipolar interaction. And, and so I was wondering how you explain that.
Okay, good question. The momentum scattering rate is not a linear function of the temperature. And also, in this material, we may not have the Dirac-Perot mechanism as the dominant mechanism. There's also the other mechanism, the Elliott-Yaffe mechanism, that's inversely proportional to the momentum scattering. So I said the Dirac-Perot, well, it's the like motion narrowing for that particular mechanism. But as I increase the temperature, which does not mean I'm increasing the momentum scattering just like linearly, or there are other factors that's contributing to the temperature dependence other than just the motion narrowing.
And what are those other factors?
That's the temperature dependence of the momentum scattering rate, say.
So your samples have a high resistivity. How are they going to function as solar cells?
Well, in the solar cells, it basically works in the vertical geometry.
Well, they don't have very far to go.
Right. Hundreds of nanometers is sufficient for the solar cell. of course, for spintronic applications, in terms of transport property, of course, if we want to start, we should also explore the vertical geometry device first. Lateral transport is too difficult.
So nobody wants to grow crystals of these?
That requires people, I mean, a lot of effort to develop, I believe.
So is
Please.
there any way to destroy these long relaxation times? Is there any way to destroy the long relaxation time by doing
Sure.
other things in it?
Sure. It's very easy to destroy the long lifetime. And
So how would you do it?
you can introduce impurity. You can do many things. I say. If the material does not crystallize very well, you destroy it. I mean, in our experiment, you easily kill the long lifetime.
Can you heal it in such a way as to shed light on what was the mechanism of it in the first place? I guess that was the question.
That's our strategy here. So we would like to tune those parameters one by one. But what's difficult is that usually when you change, you want to change one parameter, but you have very limited control of, say, you change only one parameter. Usually you change more than one parameter at a time. And then it's difficult to isolate which one plays the important role there.
So on a polycrystalline sample, it doesn't work? Like polycrystalline still works?
Yes, that's what's amazing here. Usually my impression of this spin precession in semiconductors are it works on those high vacuum grown epitaxial films. But this material at first looked to me, okay, it doesn't look very clean. Are we going to get a signal? But it works surprisingly well.
So how big are the little crystals in your polycrystalline sample?
The main is on the order of 100 nanometer. It's about 100 nanometer.
So is there any difference? Does that play any role?
So far, what we have found is that, say, from 100 nanometer to 300 nanometer, roughly, there's no change of the spin dynamics. At least down to 100 nanometer, no change.